Hi everyone, welcome to this episode of Keipert Labs. In today's episode we're going to talk about monitoring conditions in the Haber process. We're going to remind ourselves of what the Haber process involves in the production of ammonia. We're going to list out the compromise conditions that we use to get the best balance of rate, yield, cost and risk in the Haber process. We're then going to look at the different aspects of the Haber process at an industrial level that we need to be careful about monitoring in order to ensure that we're continuing to maintain this balance. So firstly, what is the Haber process? The production of ammonia from nitrogen and hydrogen gases. Hopefully you're really familiar with this by now. And so we have an equilibrium reaction. It is exothermic with minus 92 kilojoules per mole. We access the nitrogen that we need from the air, and we get the hydrogen from the transformation of natural gas in the steam reforming process. So we take methane from natural gas and combine it with steam. We produce hydrogen and carbon monoxide, which we further then break down so that it doesn't poison our catalyst to form carbon dioxide and more hydrogen gas. So the hydrogen gas and the nitrogen gas that we have then are channeled into producing our ammonia. But so, then one of the things that we mentioned in our previous video was this idea of compromise conditions. That is, we want to get the best balance of reaction rate and yield, as well as cost and risk, in terms of making sure that it's practical, economical, safe, and effective. Okay, and so some of the conditions that we pick, a moderate temperature of around 500 degrees Celsius is quite common. It gives us the best balance of yield, that is the effectiveness of the process, versus rate, making sure that it's practical. Okay, there's not much point getting an exceptionally good yield at a speed that is too slow to be worth it or viable. We also want to make use of a moderate pressure, that is around 200 to 250 times atmospheric pressure, that is around about 25 megapascals, is quite common. Okay, this gives us the best balance of cost and risk, high pressure equipment being very difficult to maintain and use and potential for danger, versus then greatest yield because of the equilibrium. And we also then make use of a magnetite catalyst because it lowers our activation energy. That is, we get the same benefit in terms of rate and yield, but at a lower temperature, because more particles possess enough kinetic energy to pass the threshold when we've lowered the threshold. You think about that idea of like taking a high jump bar and then you lower it right down. It's a lot easier to actually kind of get over that bar when we change how easy it is. So these are some of the compromise conditions that we use industrially during the production of ammonia in the Haber process. So here we have a bit of a schematic of actually kind of some of the equipment that we would use in the Haber process. Now obviously every plant that's going to produce this is going to be different in its own way and in terms of how it's actually set up. But you can kind of get a sense of how this reaction is going to happen. So firstly, we have, and what we're going to do in going through this diagram, I'm going to pick out certain points that are going to be necessary for us to actually kind of understand a little bit more about. So the first thing to see is that we get a stoichiometric mixture, excuse my fairly rubbish highlighting on here, of the reactants being pumped in. Okay, so we actually, in considering where we get these gases from, that we mix them in the right ratio of 1 to 3 moles, 1 mole of nitrogen to 3 moles of hydrogen before we actually get to our reaction chamber. So making sure that we get the right mixture here is really important. Okay, to make sure that we're minimizing the excess, that we're getting the best kind of balance here. We get the first kind of pump that we have here is what is generating our high pressure. Okay, so that's something that we're going to need to make sure that we monitor, that we're producing the right kind of pressure that's then maintained. You can see kind of down here, this is where our 250 atmospheres worth of pressure is actually going to be maintained inside. So it's important that we monitor that is continuing to work well. Okay, because if that pressure starts to change, whether it's increasing or decreasing, then it's going to affect how well this process works. Okay, so that our reactants kind of go in here, and then we can see that they split and then actually kind of travel down towards the bottom. Okay, that the heat of the reaction that's going on in here is what is going to partially heat the gas that passes by. So we're actually heating it up by making use of this extra kind of heat of reaction that's there. So we're recycling that energy, if you like. Okay, so that then, but then as the gases kind of come down, then they're actually being heated up in this kind of section here, so that we're getting that right, the temperature conditions that we want around about that 500 degrees Celsius taking place inside this chamber. So this is where the reaction chamber actually is. So like in terms of, this is where the ammonia is being produced. Okay, so this is where our, we're seeing we're using 400 degrees Celsius here because we're making use of the catalyst, and the catalyst being present inside the container. So we've produced ammonia, but we also have unreacted nitrogen and hydrogen gas. Okay, so now what we've got to do is we've got to try and refine this process. So we've gotten a yield of around about 15% of ammonia that is actually kind of been created. So the first thing that we're then going to do is we're going to pump it down through here. So this is a condenser, because ammonia turns into a liquid around about minus 33 degrees Celsius. Okay, whereas obviously nitrogen and hydrogen don't become liquids until, close to minus 200 degrees Celsius. So if we cool this down by using coolant that's going around this tube here, that then what we're doing is that we're actually converting our ammonia to liquid. So going from gas to liquid. So the liquid ammonia can actually then drain out the bottom and be collected down here. And then we take our unreacted nitrogen and hydrogen gases, and then we actually pump them back in. So in doing that, in recycling, that we get a massive increase in yield. So instead of from 15%, but we actually end up with, based off the mixture that we started with, that we can get close to 98% yield, because we're not wasting these extra gases, that we're actually channeling them back in order to produce more ammonia. We're making use of the fact that the heater reaction is actually partially heating our gas anyway, so that we're trying to be more energy efficient. Okay, and the benefit of what we're having with this condenser part of the process is that by removing ammonia from the equilibrium, we continue to drive the equilibrium to the right-hand side to replace it. That is, we're constantly pushing towards the right because ammonia is being removed from the system. Now, it's not being destroyed, but it's being removed because it's not a gas anymore. It's a liquid that's been siphoned away. And so then our equilibrium continues to create more and more and more, rather than just kind of establish this middle ground. And so there's some of the things that we need to keep a close eye on. We're trying to get the ratio of the reactants, making sure that we're maintaining our pressure and temperature conditions, using the temperature of this final heating to make sure that that's working correctly. It's also important in terms of our gas here that we don't have any oxygen present in our mixture. Because as you can imagine, if we're taking oxygen and hydrogen gases and we're heating them up together, that we have a very, very dangerous mix that will be highly likely to get an explosion. So making sure that our gas here has no oxygen present before it actually reaches anywhere near here is really important. Okay, and then being able to monitor in terms of the pressure and the composition of all of the things that are feeding back into this process, monitoring the ammonia that's produced to check and see that it's not contaminated, as well as then the gases that are pumped back in again. And then the pump, obviously, aside from getting the gases where it needs to get, where they need to be, that also helps to maintain the right pressure. So we firstly kind of reminded ourselves about what we mean by the Haber process for the production of ammonia. We looked at the nature of compromised conditions and kind of went through some of those specific conditions that we use to get the best balance of rate, cost, yield, and practicality. And then we looked at different ways and places that we'd actually need to monitor the Haber process to ensure that we're maintaining effective yield, that we're getting the best balance of economics, we're getting the best, minimize that risk, we're trying to then make sure that it's cost effective, and all of, considering up all those things. Alright, thanks very much for watching. Don't forget to like and subscribe. Bye for now.